My name is Huang. I work at CU CIRES and NOAA ESRL GSR lab, and today I'm going to talk about some work about aerosol data assimilation and reanalysis. How do I remove this? Okay, it's good. So the title of my presentation is Development of a Global Ensemble-based Data Assimilation System in JEDI for Aerosol Forecasting and Reanalysis using GEFS-Aerosols model. So this work is supported by the project that are funded by NOAA OAR. Do I remove this? Okay. By NOAA CPO MAPP program and the NOAA OAR WPO Air Quality Program and the NOAA OAR WPO GTTI program. So first, I would like to thank all the co-authors and collaborators who contribute to this work, like Mariusz and Sam, George, Lee, and Judy, and Haiqing, my colleagues from CU CIRES and NOAA ESRL GSR lab, and Cory, Andy, and Daryl from NOAA EMC, and Dan and Benjamin from JCSDA, and Shuba from NOAA Nestis, and also Alindo from NASA GMAO, and Sarah and Xingwei from University at Albany. How do I move? Oh, okay. Here's some background information. The Global Ensemble Forecast System Aerosols, GEFS-Aerosols, went operational for aerosol forecasting last September at ESRL and NCEP. This model relies on finite FV3 dynamic core and GFS physics. The aerosol parameterization is based on Goddard chemistry aerosol radiance and transport model. This model has 15 aerosol species that are dust, sea salt, 4-5 size beans, and hydrophobic and hydrophilic black and organic carbon and sulfate. A lot of processes are included in the model, such as emission, dry wet deposition, and chemical reactions. Both the natural and anthropogenic emissions are included in the model, especially daily updated blended global biomass burning emission products and fire radiative products are used in the model. In the current, the aerosol forecast from GEFS-Aerosols are not constrained by the observations, and it shows very large difference compared to NASA Mariusz reanalysis and ECMWF CAM's interim reanalysis. An example I show on the in the figure on the right. So the goal of this project is to develop a global aerosol ensemble-variational data assimilation capability within joint efforts for data assimilation integration, JEDI, to improve global aerosol forecasting and produce aerosol analysis at NOAA using GEFS-Aerosol model. Here, the JEDI is a joint effort led by Joint Center for Satellite Data Assimilation, JCSDA, and will be the next generation operational data assimilation in the US. This is the flowchart of our JEDI-based global aerosol inverted assimilation system. It has the variation component and also the ensemble gamma filter ENKF component. Here, the ENKF adopts the local ensemble transform gamma filter RETKF, which is ready in JEDI. Also, a recentering procedure is applied on the RETKF analysis and control analysis. For global aerosol data assimilation, we are going to assimilate the most commonly available aerosol optical depth retrieval AOD at 550 nanometers. To integrate this capability within JEDI framework, we process the AOD retrievals into JEDI's observation format, that is, interface for observation data access. We also developed AOD forward operator and its adjunct in the JEDI's unified forward operator component. They are further used in the RETKF and the IMVAR update. In this work, we are going to assimilate VIIRS AOD retrievals at 550 nanometer on board NOAA SNPP satellite. The AOD is a column integral type of observations, which represents the total extinction of solar radiation over a column. It can be expressed as a summation of aerosol mass mix ratio X multiplied by their corresponding extinction coefficients B and the model layer depth Z. The left animation shows an example of VIIRS AOD retrievals at 550 nanometer at about 50 kilometer resolution over the 6-hour interval. In the data assimilation, the AOD will be modeled using the 15 aerosol species I mentioned in the GEFS-Aerosols model, following this formula, and the AOD innovation will be further used to correct the forecast of the aerosol species as I shown in the figures on the right. In our data assimilation, the AOD bias and uncertainty are linearly dependent on the AOD itself. In general, the AOD has relatively larger bias and uncertainty over the land compared to the ocean areas. In the current, the AOD forward operator can be calculated using NASA lookup tables and NASA lookup table from CRTM in JEDI. Here's a comparison of these two forward operator calculation. So the top figure shows an example of the VIIRS AOD retrievals at 550 nanometer in June 19, 2016. And the bottom two figure shows the modeled AOD from CRTM lookup table on the left and from NASA lookup table on the right. So we can see that NASA lookup table actually did a much better job in modeling the AOD retrievals. We also developed stochastic perturbed emissions based on ECMWF's stochastic perturbed emission parameterization tendency scheme. Here, I would especially want to thank one of the co-authors, Trahan, who implemented this method in the GEFS model. The SPE method here actually serves for two purposes. The first one is to correct model bias by scaling the emissions. The reason why we're trying to do this is because the variational bias correction in JEDI is not ready, so we just use this one as a temporary solution to correct the model bias. So in the GEFS-Aerosol model, there are four major emission sources that are dust emission, anthropogenic emission, wildfire emission, and sea salt emissions. As you can see, at least in here, different emission sources dominate over different areas. For example, dust will dominate over North Africa and the Middle East areas. To determine the scaling factors for each type of emissions, we calculate the AOD over different regions, as I shown in the top left figure, and also listed on the x-axis of these bar plots. So here, let's look at the red bar and green bar. The red bar shows the regionally averaged AOD retrievals, and the green bar shows the averaged modeled AOD retrievals. By comparing the green bar and the red bar, we can see that the modeled AOD in general shows very severe underestimate compared to the AOD retrievals. So we decided to initially set the emission scaling factor to 2. That means we're going to increase the emissions by a factor of 2, which is shown in the blue bar. We can see that in general, the height of the blue bar roughly doubles the height of the green bar. This is within our expectation because we set 2 as the emission scaling factor. The second purpose of SPE is to perturb the emissions so we can increase the spread. The left animation shows an example of sea salt emission spread. And to calculate the emission perturbation standard deviation, we first calculate the modeled AOD RMS error and spread from 20 members, as shown in the light green and dark green bar correspondingly. We can see that our system actually, for almost all the regions, we can see that our spread is insufficient. So by comparing the light green and dark green, we decided to set the emission perturbation standard deviation as 2 to increase the spread, and the resultant RMS error and the spread are shown in the light blue and dark blue bars. If we focus on the green bar, dark green and dark blue bar, we see that it seems that the spread does not increase that much. The reason is because when I calculate the spread, we include observation errors. In our current assimilation, the observation error is kind of large, so you don't see a very sharp jump from the green bar and to from the dark green bar to the dark blue bar. If I remove the observation error from the spread calculation, we can see a clear spread increase. So this is just our initial tuning for the scaling factor and emission perturbation standard deviation. We may need to further refine these factors. Here comes our experiment design. We will run 6-hourly assimilation of AOD retrievals at 550 nanometer derived from NOAA VIIRS onboard Suomi NPP satellite using 3D INVAR and RTKF for aerosol update. And also a recentering procedure is applied on the RTKF analysis and also INVAR analysis. And also we are going to use NASA lookup table to calculate AOD forward operator, which as I shown earlier, it shows a much better agreement with the AOD retrieval themselves. Here also I wanted to mention that the meteorological variables are corrected by adding regraded increments from operational GEDAS analysis. That means the meteorological variables are not updated in our aerosol data assimilation step. And also we run one control plus 20 member ensemble forecast at a resolution about 100 km using GEFS-Aerosols model. Our 1-month cycled VIIRS AOD data assimilation experiment starts after 3-week free model run in May 2016 and goes through the whole month of June 2016. The statistics will be performed for the last 3 weeks of June 2016. So this table summarizes the 4 experiments we performed for this work. The first one is no DA. That means there is no aerosol data assimilation. Only the meteorological variables are corrected by the GEDI analysis. In the DA experiment, it will include the aerosol data assimilation, and the NTF ran 20 members. The DSP actually is similar to DA, but applies the stochastic perturbed emissions, and with all the emission scaling factors and emission perturbation standard deviations equals to 2, as I showed in the last slide. The DSP3 is similar to DSPE, but for the increased ensemble size from 20 to 60 by including ensemble forecasts at plus and minus 3 hour valid time. The goal is trying to cheaply increase ensemble size and hopefully increase the spread of the ensemble. This slide shows some innovation statistical results by comparing the background or 6-hour forecast and analysis with the VIIRS AOD retrievals. The left bar plot shows the average bias over the last 3 weeks of data assimilation, and the red bar plot shows the corresponding RMS errors. We can see that compared to the no DA, the blue bar 6-hour forecast, assimilation of AOD is able to efficiently reduce the negative bias and the RMS errors, both in the background and also the analysis. And also we can see that after 6-hour forecast, still the data assimilation maintains about probably like about 35 improvements relative to the no-DA experiment in both in the background. We also see similar results when we verify against independent modest AOD retrievals. Here, I wanted to comment that when the variational bias correction is ready in JEDI, we expect it will be able to further reduce the bias in our AOD data assimilation experiments. We further compared the background ensemble error and spread in the 3 data assimilation experiments. As in the scattering plot, the x-axis of the scattering plot shows the spread, and the y-axis shows the RMS errors. And the samples are collected over the selected 11 regions, and each region has about 24 samples. As we can see that after we apply the SPE, the background shows improved background error and spread consistency, especially for the samples over the land. When we increase ensemble size from 20 to 60, we see further improvement especially for the samples over the East Asia. This slide, this time series plot compared globally averaged AOD with independent NASA MERO2 reanalysis in black and ECMWF CAMS interim reanalysis in gray. We can see that the no DA 6-hour forecast in blue curve actually shows severe underestimate compared to these 2 sources of reanalysis. After AOD did assimilation, like the warm colors, we can see it significantly improved the AOD, especially when the SPE and when the stochastic perturbed emission is applied and the ensemble size is increased. This 2D map plot shows the bias of the no DA 6-hour forecast, no DA analysis, and the DSP analysis against NASA MERO2 reanalysis in the first row and against ECMWF CAMS interim reanalysis in the second row. So we can see that the analysis in both DA and DSP experiment are able to efficiently reduce both the negative bias and also the positive bias that shows up in the no DA 6-hour forecast. After we apply the SPE, actually its analysis further reduce the negative bias. Here I wanted to comment that the analysis from DSP3, which are not shown here, it shows very similar bias patterns as the DSP3, but it slightly further reduce the bias over these coastal areas. In this slide, we further compare the global aerosol profiles with the NASA MERO2 and the ECMWF CAMS interim reanalysis. Here, for these 4 major aerosol species, I selected one areas where this aerosol is dominated. So in general, we can see that the no DA 6-hour forecast in blue, in general shows underestimate compared to the independent reanalysis from NASA and ECMWF. After assimilation of AOD, we can see clearly improvement of their profiles, which has a better agreement with the reanalysis, especially when the SP is applied. In this slide, we are trying to understand how the scaling perturbations and perturbing perturbations contribute to the improvement of the DASP experiment and over D experiment. I think I'm just gonna jump to the conclusion here. So our conclusion by comparing the experiment with only scaling the perturbation or only perturbing the emissions in the DSP, we found both scaling perturbation and perturbing, both scaling emissions and perturbing emissions contribute to the improvement in the DSP experiment. Especially scaling emissions contribute more. I think this is expected because our model itself already has very severe negative bias in here. Another point I wanted to point out is that assimilation of AOD retrievals is more efficient to reduce bias and RMS error compared to only increase the emission of free model forecast. Here's the conclusion. The JEDI-based aerosol data assimilation is being developed to improve the aerosol forecasting and produce aerosol reanalysis using NOAA's GEFS-Aerosol model, and the stochastically perturbed emission are developed to correct model bias and background ensemble spread efficiency. Our cycled experiment shows positive impacts of assimilating AOD retrievals in the model. The following list are ongoing and future work here. I wanted to emphasize two of them. The first one is that given that our current evaluation is only 1 month, which is kind of short, and we are preparing to implement AOD data assimilation for near real-time run at NOAA, ESRL, and JSR lab. The other one, we are working on developing softwares to verify modeled AOD against AeroNet observation at different wavelengths. This will give us more confidence about the performance of our data assimilation system. And the rest of it is we are further to improve the system by developing the dual resolution capability and developing the static B and applying the variational bias correction when available in JEDI. And in the future, we would like to also accounting for the non-Gaussian error distribution. The last comment I wanted to give here is that even though this session is for the coupled data assimilation, and we are also interested to explore like the coupled aerosol and meteorology data assimilation in the future. I think this is my last slide. Thanks for your attention.
Thank you, Bo. A very nice presentation.
Thank you.
It looks like we have one question ready and another one is in writing. So I'll read the first one from Sergey Frolov. He says, nice talk, Bo. For slides 11, how do you explain the dipole around equator in the bias for DA runs? Thank you.
The dipoles, you mean this on slides 11, the dipoles like here and here. I think these areas actually you can see these areas.
Actually, on the top row, the yellow and green dipole.
Yellow and green. Okay. For the I think from the no free forecast run, I think for the yellow one is correspond to the dust aerosol species over the North Africa, and dust actually play a very kind of like dominant role in the AOD calculation of that areas. In that model, when we don't apply the, when we don't assimilate the AOD data assimilation and either don't scale the emissions you can see in the free model run, it has very large underestimate of this AOD. It means that our model itself has a very low emission for the dust in there. For the dipole one, it's in these areas, it corresponding to the areas we may have some fire in there, but kind of like in these areas, the AOD is overestimated. If we look at the bar plot in here, in the South Africa and tropical in here, we can see that the green bar, actually the modeled AOD, is very similar to the observed AOD in red. After we scale the emissions, actually we see overestimate of the AOD in here. But we have not found a good, because Because over the wildfire emission distributed over different areas, we haven't found a good way trying to like give different scaling factors over different areas. But I think it's doable in the code, in the SPPT code, but we haven't implemented that yet. I think, do I answer your question?
Okay. Okay, thank you. And you have a second question that's from Shuguang Wang. She says, great to see the valley time shifting is used to populate the ensemble in the AOD assimilation context. How is your result dependent on the length of the shifting window?
Oh, thanks for the question. We just started this one. We haven't exactly tuned like how the applying different shifting time interval for this one. It would be very interesting to see the results by applying different like 1 or 2 or 3 hour shifting time interval. That would be very interesting. Thanks for your question.